Greetings, everyone. I had a little bit of difficulty with the camera angle during the live recording of Lecture 2, so I'm going to do this re-recording. You won't have me pointing at various things on the screen, but I think this will be a better review in terms of being able to see what's on the slides. So just a reminder of the reading. It's the same as we had last time, Chapter 1, and a bit of chapter 16 in the 10th edition. Today we're going to talk about several topics related to water. We're going to discuss the hydrologic cycle, the residence time concept, an introduction to water quality parameters, especially total dissolved solids. We'll talk a little bit about drinking water, and then we're going to switch gears and talk about motions within the hydrosphere and atmosphere reservoirs. So just a reminder, there's still time to get in on the poll about entirely live lectures versus some content delivered by pre-recorded video. All right, so these are just some various images of water in all its various forms. As it says here, I think water is possibly the most important chemical compound on Earth. It's involved in a critical way in the hydrologic cycle, in the rock cycle, in the biosphere, in ecosystems in general. And you see here various forms of water, including liquid, solid, and vapor. And in fact, transformations between these forms are what are responsible for the hydrologic cycle even existing. You also see this example of the water molecule. If you recall, water is H2O. The tiny little gray dot there in the middle is meant to be an oxygen atom. Oxygen comes with 6 valence electrons, and we park 2 hydrogen atoms next to it. We make 2 bonds. Each of those hydrogens are shown here in red. And the type of bonding hybridization, and this is something that you can check out in the review pack, is sp3, which means there's a tetrahedral coordination between each of the bonding orbitals. Now, because molecular water has oxygen at its center, which comes with 6 valence electrons, and a filled Lewis shell gives it 8 electrons, we end up with 2 pairs of unbonded electrons. Those are shown in purple there, that occupy 2 of those 4 sp3 orbitals. And this arrangement gives the molecule a partially negative charge on the side where the unshielded electrons are sitting, and a partial positive charge on the side where the hydrogens are sitting. This makes water a polar solvent. It's also what makes water be a liquid at room temperature, even though it's got a very low molecular weight. Think about the molecular weight of 18 and compare to that to things that are gases in our atmosphere, such as carbon dioxide and nitrogen. Those molecules don't bond together by any means, whereas water molecules do by hydrogen bonding, which gives it some kind of stability and structure that allows it to stay in the liquid state at a much higher temperature than things with similar molecular weights. So water interacts significantly with every sphere of the cycles we talked about last time. And importantly, the exogenic, remember, exogenic means exterior part of the Earth, not counting the interior, water cycle effectively transports a wide array of both essential and hazardous chemicals within the natural spheres and to and from the anthrosphere. And I've just reminded you of something we talked about last time, which is that we can divide up reservoirs, we can divide up various parts of reservoirs into sub-reservoirs, and consider the motions of things between them as going between the reservoirs themselves and fluxes, which are the transports, which are given in units of mass or grams or concentration units per time. Now, water moves throughout the hydrologic cycle due to variable heat inputs and losses across the globe, which set up thermal gradients that cause convection within some reservoirs. And this, of course, is what fuels the evaporation and precipitation. This, plus the forces of gravity and buoyancy, create the water cycle. Just to remind you of the phase diagram, this is a pressure-temperature diagram, pressure on the y-axis, temperature on the x-axis, and this goes to very high pressures and very high temperatures. We're used to looking at the part of the diagram down in the lower left-hand corner. Remember, room temperature is 25 degrees C, right? So that would be 298 K. Freezing is 273 K, which is shown here on this diagram. And that triple point, the place on the diagram where solid, liquid, and vapor coexist, actually happens on Earth. And when we move along any of the lines on these diagrams, for instance, the line that it separates liquid from vapor, anywhere along those conditions, we will have evaporation and precipitation, which are the forward and reverse direction reactions of water going from the liquid to vapor and vice versa. And along this kind of nearly vertical line, we can have that separates the field that says ice one from liquid water. We can have melting of solid that goes to liquid. We can even, at times, even though it's not shown on the phase diagram, have non-equilibrium conditions where we have what's called sublimation, where solid can evaporate straightly into vapor in very undersaturated situations at very great coldness or very low temperature, such as over glaciers. Here's a bunch of other properties. This is a table from your textbook. On the left-hand side of the table is the property, and on the right is the significance of that property. So obviously it's an excellent solvent. It's got a high dielectric constant. It's got high surface tension. And these things control the ability to solubilize nutrients and waste products and other chemicals, as well as ionic substances. And the surface tension basically controls the way water behaves in biological tissues, in cells, for instance, as well as how it wets surfaces, flows between grains, for instance, in the subsurface and groundwater, etc. It's transparent to visible light, which is, of course, important for supporting photosynthesis and allowing light to penetrate into bodies of water and help heat them up at their surfaces. Interestingly, it's got this maximum density as a liquid at 4 degrees C, which means that ice floats. So bodies of water freeze from the top down. This only applies to fresh water, as we will see later today. Salt water doesn't do this. But importantly, water that is colder than 4 degrees C, meaning anywhere between 4 and 0, which is the freezing point, is less dense than water at 4 degrees C. And water that's obviously warmer than 4 degrees C is also less dense. And this will become important when we look at how bodies of water stratify and then circulate in the presence of temperature changes. Now, there's three other aspects that are highlighted in red here: the heat of evaporation, the latent heat of fusion, and the heat capacity, which basically collectively determine the stability of water in the various conditions that we happen to find at the surface of Earth that allows it to transform between the three main forms that we talked about on the prior slides, thus setting up the water cycle. So this is a kind of a introductory geology version of the hydrologic cycle, right? And I'm sure you've all seen these before in some way, shape, or form. Water evaporates from bodies of water. It goes into the atmosphere, it condenses, precipitates out either as rain or snow, or perhaps hail, something like that, falls on the land surface and either accumulates and then melts and flows off, or just flows off directly if it forms as liquid water. There's also, of course, evaporation from various reservoirs on the land surface, and anything excess of this flows back out into bodies of water, eventually reaching the oceans. Of course, human activities tend to also disrupt the water cycle. And in a net sense, one of the things that humans tend to do is evaporate water. We collect water, we move it around, maybe we use it in agriculture, maybe we use it in cities. However we're using it, a significant fraction of what we use goes back up into the atmosphere, leaving the runoff from human use traditionally much saltier or higher in dissolved solids than the source water that we took in. And we'll talk about that detail more. But I also want to point out one final thing, which is that some water percolates into the ground and then flows along gradients that are driven by gravity to either poke out on the land surface in a well or other kind of spring, and or flow directly towards the ocean. Now, this is a table. There's actually two tables here from two different sources. They're both books I used to use for this course back in the 90s. And importantly enough, the source of data from both of these tables is the same. And I give you both tables just to help illustrate that numbers on tables like this are come with a little bit of uncertainty and a little bit of how they are interpreted. So we don't want to overinterpret the data. For instance, if you look at the volume of the oceans, you'll see that in one of the tables is 1.37 times 10 million cubic kilometers. And in the other table, it's 1.40 times 10 to the 6th cubic kilometers. And I'm noticing an error there. It says 106, but that should be 10 to the 6th. So, both of those numbers are the same within air at approximately 1.4. But it's important to recognize, as I say, the small amount of uncertainty. We have to look at these numbers. They change throughout climate cycles. They're changing now as we, heat the planet. They've changed during glacial, interglacial cycles. So these are approximate. But notice that for the exogenic water cycle, something like 96 or 97% of all the water is in the oceans, right? And this is salt water. So then the next biggest category are ice sheets and glaciers. Depending on which table you look at, is somewhere between 2 and 3%. So between those two things, that makes up the lion's share of all the water, nearly 99% or more, depending on which table you look at, which means that everything else accounts for about 1%. Okay. And that everything else is the water we use to sustain ourselves, whether it's groundwater, whether it's lakes, rivers, soil moisture, atmospheric water. You can see those numbers get very, very small. I give you this to illustrate the very precious nature of these resources. These are the things that we use to sustain our, way of life, as well as our ecosystems and natural ecosystems. Hopefully there's something left over for them. Our agriculture, our industry, everything pretty much depends on that sort of 1-ish% that isn't in the oceans or ice sheets and glaciers. And a lot of the groundwater that's deep is too deep to economically be recovered. So that even further reduces the fraction we have available to us as humanity. Okay, so this is another version of the hydrologic cycle with some fluxes on it. It's basically got the same numbers as the table that was on the right-hand side of the previous diagram. You'll notice a couple things here. Reservoirs are given in parentheses, and you can see if you look down in the caption, you'll see that the inventories or the volumes of these reservoirs are given in 10 to the 6 cubic kilometers, which also happens to be 10 to the 18th kilograms, if that's easier to comprehend unit. Both of these are huge numbers. And the fluxes, which are shown as arrows, are given in units of millions of cubic kilometers per year, or 10 to the 18th kilograms per year. So the first thing you notice if you go and look over the oceans, you'll see that evaporation and precipitation over the oceans are pretty large and nearly balanced. But there's a little bit more evaporation than precipitation. And that net difference translates into a small amount of vapor transport from the oceans to the land. And in fact, if you add up those numbers, you'll see that 0.036, which is the vapor transport, is exactly the difference between the precipitation minus evaporation over the ocean. This is a balanced cycle where these numbers have been purposely modified to make them come out with no net gains or losses in the cycle, as I mentioned in lecture 1. You can also see there's some evaporation and precipitation over the continents. And again, there's a slightly less evaporation and slightly more precipitation over the continents. And those numbers also balance out to the 0.036 that's in the vapor transport. You'll also finally see a value of runoff as 0.036. And that runoff I put in quotes because it includes both surface runoff as well as discharge beneath the land surface as submarine groundwater discharge if the groundwater reaches all the way out into the ocean. Now, of course, we are very interested. This is a globalized value, but we're very interested in how the cycle might operate in one place or another, such as the island of Oahu, or all of Hawaii, or the Pacific Rim, or North America, or Australia, or any other region you can conceive of, because if in a particular place these fluxes are not balanced, this gives us an idea about the extent to which human activities can superimpose on these natural fluxes to change them in a way that would sustain populations. In some places, especially very arid regions, where these fluxes tend to be quite low, there's a lot less flexibility in humans taking water out of the landscape for human use before we start to perturb various aspects of the natural system. So this is another view, a perhaps drier view of that same diagram where I more closely highlighted the reservoirs in boxes and the fluxes as arrows. So we can take that hydrologic cycle, as I just showed you before, and think about it as three kinds of reservoirs. We have the atmosphere, which is kind of a special reservoir. Water doesn't spend very long there, but it exists in all three of the states that water can exist in. And then we have surface water that sits in very large bodies, the oceans, of course, as well as lakes. And I call these geographically fixed holding tanks. Water tends to spend a fair amount of time there and accumulate compositional attributes because of it. And then pretty much all the other reservoirs I consider migrating reservoirs. Water goes into those things and it moves relatively quickly across the land surface. It can also develop compositional attributes from that, but the main point is that water that's in a migrating reservoir typically represents a flux. It's not only carrying water, but all sorts of dissolved and particulate chemicals from one place to another. And these types of bodies of water are the things that represent a lot of the fluxes in the diagram that I showed you on the preceding slide. Whereas the holding tanks represent large reservoirs. They can also have fluxes within them. Think about things like the formation of shells and biomass by organisms, production of oxygen, the consumption of carbon dioxide by photosynthesizing organisms, for instance. Those can change the composition of things within the water without changing the amount of water in the reservoir. And we'll talk about this more as we go along. You'll also notice that I put glaciers in migrating reservoirs. They tend to move relatively slowly, although as time goes forward with global warming, they're moving less slowly than they were in the past. But they do tend to, in a grand scheme of things, represent a relatively small flux in terms of movement per year. This is another view of the water cycle. And what you're seeing in this diagram now, the arrows are scaled in their size by the flux, the amount of water that moves. And you can see that there's quite a wide range of values in terms of these happen to be given in cubic kilometers. This has a slightly more refined version of the water cycle than the flux diagram I gave you a few slides back. The numbers are a little bit different, but they're close, and they represent the sort of estimates of the balance at the time that this diagram was made. There's also a few other subtleties in here, such as the oceans are shown as shallow and deep water, and we'll talk about that in a moment. Okay, so the next thing I want to bring up is the concept of resonance time. I asked in class if people were familiar with this, and everyone pretty much nodded their head. So I'm going to go through this pretty quickly. Resonance time is a concept. It tells us on average how long something spends in a reservoir. It's a concept. It doesn't really hold rigorously anywhere, in part because for resonance time to rigorously hold, we have to have a steady state condition where the flux of something into the reservoir and out are equal, meaning the reservoir isn't changing size. In those conditions, resonance time, which is sometimes written as the Greek letter tau, or sometimes the capital letter T with a subscript res for resonance time, those are two common ways to write it, is calculated as the reservoir size, which I've shown here as A in brackets. And as remember, I've mentioned this before, reservoirs can be things like volumes or mass of water, or it could be concentration units like moles of sodium ions in the ocean. The flux is in the same units of volume or mass or concentration per time. And so in a case where the flux in or out is balanced, the resonance time is stable, and we have an equation where the reservoir over dA dt, which is the flux, tells us a value. Now, we can find conditions where, for instance, maybe a lake is being drained because humans are taking some extra water out to use it in a city, or we've got a particularly rainy period of time, such as happening right now in the western part of North America, and so reservoirs and lakes and so forth are filling up, in which case the flux in is greater than the flux out. We can still calculate a resonance time. Oftentimes we'll calculate the resonance time using the input flux and the output flux and look at how far out of balance they are. so that even though we're not getting a precise number out of them, and you can, in fact, take the average if you want to find something that you think is closest to reality for that snapshot in time, but it gives us an idea of the scale, meaning does water spend hundreds of years, thousands of years, days, minutes, hours, whatever time frame you want in that particular reservoir. It gives us an idea of the time scale over which it's that in that reservoir and has time to develop composition. So this is just a hypothetical scenario. I've made a lake called Lake Clear and Fresh with some fluxes in and out, shown here in green for the fluxes in and red for the fluxes out. And if you look at this quickly, you'll see that they're basically balanced. I did this on purpose to make the calculation as simple as possible. These are in units of M-L, which is my shorthand for millions of liters. So these are smaller units than we've seen in some of the other tables because we're talking about a lake and I wanted it to be simple. So we've got a lake volume, we've got river and rainfall inputs, we've got evaporation, river output, and groundwater output for the exit fluxes. So we can add up each of those fluxes, which are done here on this table. And you can see here that in both ways, the flux in and the flux out is 60 million liters per year. So the volume of the lake is not changing, it's constant. And we can calculate a residence time by taking 1,000 million liters, dividing it by the 60 for the flux, and we come up with 17 years. So on average, the water in this lake would be 17 years old, which gives us a useful indication of how long it might take to flush a contaminant out of a lake, or how long it might take to replenish a lake if water levels were taken severely down by drought, etc. So this is an average estimated across the entire hydrologic cycle. If you go to individual lakes or swamps or ice caps, you will find a big variety in these numbers. But like I said, these are averages. They show you that where water spends most of its time. On average, it only spends about a week in the biosphere, meaning it goes in and out frequently. In the atmosphere, it's about the same, 1.5 weeks. In river channels, where it's flowing relatively quickly, only a couple of weeks. Swamps, maybe 1 year to a decade. Lakes and reservoirs, we're talking about the time scale of decades. Soil moisture, weeks to perhaps a year. And then we get to the big ones, ice caps and glaciers, where it's thousands of years. The oceans is many thousands of years. And some groundwater, especially the deeper we go, multiple kilometers beneath the surface, we can get to water that is as old as 10 or maybe 20,000 years. And these are things that you can determine in various ways, such as radiocarbon, which is something that exchanges with the atmosphere where we have constant production of radiocarbon. And once we isolate the water from the atmosphere, the radiocarbon starts to decay. And this is one of the ways we can calculate these kinds of residence times. Okay, so the next thing we're going to talk about a little bit is water quality. And one water quality parameter, perhaps the most general one, is called total dissolved solids, abbreviated TDS. You'll see me use it a lot. If you get your Board of Water Supply report here from Honolulu, you'll see TDS on there. TDS is kind of a garbage can term in the sense that it tells us nothing about what the chemicals are, what the dissolved solids are. It just tells us how much is there. And it's important because it affects physical parameters like the viscosity of the water and its density, and things like its boiling point, amongst various other things. And it reflects a whole range of processes, which will largely be the topic of our next lecture, lecture 3. But I've listed some of the topics here just to get you thinking about it, such as the relative amount of precipitation and evaporation, interactions of water with solids on the land surface, weathering, and various other kinds of reactions, which we'll talk about next time, the temperature of the water, the pH of the water, solubility of gases, oxygen, carbon dioxide, nitrogen, etc., as well as biological phenomena. So here's a table which shows you average residence times and the total dissolved solids in each of those materials. And as I sort of alluded to earlier on in this presentation, the longer water spends in a place, the more likelihood it is to gain compositional attributes, and in this case, have higher total dissolved solids. So you can see as we go from rain to rivers to lakes to the oceans, the time scale for residence goes up and the total dissolved solids goes up as well. Okay, so one way to think about TDS is to say when it's low, it's basically close to pure solvent, meaning there's very little stuff dissolved in the water. And when it's high, there's a lot of stuff in solution. So there's a lot of stuff dissolved in the water. And TDS gets to a certain point, and then we start to reach saturation of the various chemicals that are dissolving in the water, and then we can therefore put no more stuff into solution. And those kinds of conditions are pretty rare. For instance, the oceans are not saturated in the main ions that make up seawater: sodium, chlorine, magnesium, and sulfate. We could add more if there was more to add, or we can evaporate some water out of the oceans, and they're not going to come out unless we do extreme evaporation. So some examples of how dissolving stuff in water affects properties. I've shown you here, for instance, the density. We talked about pure water has a density of 1 in kilograms per liter or grams per cc, however you like to think about it, at 4 degrees C. Well, let's think about seawater. It has a mean density of about 1.034 kilograms per liter. So the way we can think about that is two components: pure water at a kilogram per liter and solids at 0.034 kilograms per liter. 0.034 kilograms per liter is also 34 grams. Now, 34 grams is a lot of material. That's several tablespoons worth of solid dissolved into that water, and it obviously changes its behavior, including making it significantly more dense, about 3.5 times denser than typical fresh water. It also, having salt dissolved in water, affects the solubility of things. Maybe some sparingly soluble chemicals don't like to dissolve very much in the presence of chlorine, chloride ion. For instance, silver chloride is a solid that comes out very copiously when there's just a little bit of chloride around. Barite, or barium sulfate, is another example of a salt that has a very low solubility constant, which means that in the presence of sulfates, such as the copious sulfate that exists in seawater, adding a little bit of barium makes most of the barium come out as barium sulfate, which is also known as barite. Whereas in a body of water that doesn't have much sulfate, barium can exist to much higher solubility. So TDS also affects usability for urban and industrial settings because, for instance, think about salts within pipes that go into an electric generation system where we're making steam, or a boiler, or anything where water is flowing through pipes where there may be some evaporation that can cause salting out in the pipes and therefore affecting the flow and everything else. So this is a table that shows you the TDS values by definition for different types of water. So what we call fresh water has anything less than 1,000 milligrams per liter, or 1 gram per liter, if you want to think about it like that. We call brackish anything between 1,000 and 10,000 milligrams per liter. Saline or salt water between 10,000 and 100,000. And remember, the example I just gave you for average seawater in these units would be 34,000. And there's something called brines, which are saltier than 100,000. Brines sometimes exist at the surface, but they're actually more common in the subsurface. Geothermal waters, for instance, found driving geothermal systems here in Hawaii or Iceland or New Zealand or wherever else. These can be very salty solutions, in part because they exist at high pressure and high temperature. Now, fresh water in the environment, as defined by this table, and fresh water for human use have really different working definitions. As we'll see on the next slide, even something as low as 200 parts per million, which is, just 20% of the maximum value to still be called fresh in the environment, is acceptable for any kind of human use. So this is a table where I've taken that 1,000 and I've chopped it up and just shown you the parts and units of sort of fractions of 100, except we've also further broken out 0 and 50 for TDS and what is good for. So drinking water is basically 0 to 50. So even lower than the 0 to 200 I mentioned on the last slide, and way below the 0 to 1,000 for the definition of fresh water. Now, if you get mountain spring water, mineral water, something like that, it can get up to about 100, okay? And this would be considered hard water. I, for instance, spent a lot of time growing up in Southern California and in San Diego in particular, where most of the water is brought in open channels from the Colorado River, hundreds of miles to the coast, where a lot of the water evaporates. By the time it gets there, it's very hard, very salty. It makes deposits in the shower. It's real hard to shampoo with and so forth. And so the harder the water, the more likelihood that it needs to be extra purified. before it can be delivered to customers. And we'll talk about that later in the semester when we talk about water purification. And anything above 200 is really considered marginally acceptable for human use. And I've also put on a little bar here, which represents about 0 to 20 or 0 to 25, which is the typical value for deionized water. For instance, if you turn on one of the DI taps in the post building or MSB or anywhere else on campus, that's basically what you're looking at. So now we're going to spend the rest of the time today talking about motions and stratification within the hydrosphere. And we'll come back to talk about composition and all the other things I touched on just before in the coming week. But we now want to think about what happens when water, whether it's in a liquid form or the vapor form, spends a lot of time in one place. Two things can happen. One thing is that it can stratify, meaning become layered with respect to density, and the other thing is it can have motions. And those motions take two forms: motions along its surface and motions in the body or the interior of the water, which are largely driven by convection. They're much more three-dimensional. And importantly, in many large bodies, whether we're talking about the oceans or even the atmosphere, the surface convection and the deeper convection can be decoupled. They can move on different time scales and have different impacts. Now, when we think about bodies of water, we think about the surface being the top of the body of water, right? The surface of the ocean, the surface of the lake. For the atmosphere, and I have to emphasize here, we're going to focus on the troposphere, the lowest layer of the atmosphere below the stratosphere. This is where most weather happens and most of the water cycle is restricted. We'll talk about higher layers of the atmosphere later in the semester. For this reservoir, the surface, quote unquote, you can't see me, but I'm using air quotes, is actually the base layer, right? What happens near the surface of the earth is where we have excuse me, the equivalent of surface motions that in the air take the form of winds. We also have convection within the troposphere, which are vertical and horizontal currents, which move up and down from the base of the atmosphere. And we'll talk about those things coming up. Now, we also know that the hydrologic cycle can be divided up into various kinds of sub-reservoirs. And in some cases where the stratification and the different types of convection causes, in effect, water masses to behave as multiple different water masses. The oceans are a perfect example. The surface oceans and the deep oceans generally don't communicate with each other except at very extremely high latitude near the poles. We think about them oftentimes as sub-reservoirs, meaning shallow water and deep water. We find this as well in lakes, as we'll see in a moment. I just want to remind you that most of the motion that we have in the hydrologic cycle, including in the atmosphere, comes from heat, and 99.98% of that heat comes from the sun. There are a little bit of heat that is added to the system from tidal dissipation in the Earth-Moon system, as well as radioactive decay of radioactive materials, both in all of the various reservoirs, geosphere, hydrosphere, atmosphere, and biosphere, but they account for something like 0.2% of the total. So it's this heat input which drives motions and therefore the hydrologic cycle in itself. Now, if you think about this, we know that not all locations on Earth receive the same amount of sunlight in a given day. There's a lot of seasonality to it, and there's a lot of variation with latitude, which is shown on the next slide. And if you, or excuse me, one more slide coming up. The first thing I want to kind of remind you is that regardless of that distribution of heat, coming from one place or another as a function of the seasons and latitude and longitude, is that for the most part, because the heat is coming from the sun, sunlight hits the surface of the earth and then reflects back out into space, and it actually changes its wavelength a little bit. It becomes longer wavelength, more in the infrared. And then as it transits through the atmosphere, it heats it up from below. So the atmosphere is kind of being heated like a pot on your stove from below, whereas the bodies of water are being heated from above. It's as if you were taking a blowtorch and blowing on the top of a pot of water instead of from the bottom. So if you think about it, things that are less warm and things that are more warm are less things that are less warm are more dense, and things that are more warm are less dense at a constant composition. So in these conditions, our atmosphere is lower density at its base than the stuff above it. in the troposphere, which tends to, things that are less dense rise through buoyancy forces. So this tends to set up convection. And in the oceans or lakes, because they're being heated on the top, this tends to impede convection because the hot water, which is less dense, is already sitting on the surface. Now, we know the oceans and lakes convect, but it needs some other processes to make it happen, which we'll talk about in a moment. So first, thinking about the way Earth orbits around the sun and the tilt of the Earth on its axis towards the sun, we get different amounts of light at different latitudes throughout the year, right? So during the Northern Hemisphere winter, there's a lot less light than there is in the Northern Hemisphere summer. Thus, the length of day changes dramatically. It changes a lot less between the Tropic of Cancer and Capricorn, right? Like here, our average days in Hawaii go from something like 11 hours to 13 hours. These are approximate numbers from the shortest to longest. And so we have more uniform heating. And as this heating varies, we also have variations in the heat content in surface bodies of water, as well as heat content at the base of the atmosphere. So if we think first about the atmosphere, we have this heating. It's variable, of course, different places on Earth, as the last slide showed. But this tends to cause some of the air masses to become buoyant and rise up above the surface. The Earth is also spinning, and so because of its spinning, we have the Coriolis effect, which tends to bend the motion of things to the right as it's flowing. And so, it's actually to the left in the Northern Hemisphere. And so this is what gives rise to the sort of the trade winds, these sort of northeasterly shapes in the Northern Hemisphere, and they're southeasterly, meaning they come from the east and go, and from the south in the Southern Hemisphere, they come from the north and the east in the Northern Hemisphere. And these are counteracted by winds that move in opposite directions at higher latitudes, as well as, again, easterlies in the polar regions. And the variations in heating and cooling and the relative differences in the density of air masses between them causes circulation patterns where we tend to have more air rising near the equator, for instance. It rises and it starts to cool as it rises. It starts to lose some water, which causes precipitation to come out. And then the air starts to circulate to higher latitude, continuing to cool. At some point, it gets dense enough, it cools and reaches back down to the surface and sets up, for instance, this thing that's labeled Hadley cell. There's another kind of circulation pattern in temperate regions called Ferrel cells. So it's this upward circulation above the Earth with the Coriolis effect that together give us these zones of easterly and westerly winds. And importantly, they also affect where on the planet we get a lot of rain and where on the planet we don't get a lot of rain. As you think about the arid bands on the planet, for instance, where's the Sahara Desert, where's the Southwest, where's Australia, they tend to sit in those places where we have descending air masses at the bases of the Hadley cells, where the air is relatively dry, which is what contributes to that aridity. And this is just a little bit more explanation of how these Hadley cells work. Now, when we look in the surface oceans, the water masses are moved about in the same direction as the winds. However, because the ocean basins are contained within continents, and because the wind that flows over the continent is a little bit more complicated because we've got things like mountains that are sitting as obstructions, we find what we call gyroscopic flow. So for instance, in the Northern Hemisphere, we have a zone where the northeasterlies are driving the ocean currents from the northeast to the southwest, where I'm pointing with the mouse now. And then there's a return flow in the zone of the westerlies where the water is moving from the southwest to the northeast. And you see the exact same thing in the Southern Hemisphere. You see the same kinds of gyroscopic flow patterns in the North and South Atlantic, as well as in the Indian Ocean. And so in the Northern Hemisphere, this pattern is clockwise, and in the Southern Hemisphere, it's counterclockwise. And the thing that connects the two opposing currents are on the eastern sides of oceans, which are the western sides of continents, we have currents that bring relatively cool water from high latitude down towards the equator. The California current is a good example of this. And on the western sides of oceans, we have what are called western boundary currents, which take water from low latitude and bring them along with heat to high latitude. The most famous one of these currents is the Gulf Stream that goes along eastern North America, but there's also the Kushiro current, which is labeled here, which goes equivalently south of Japan. And so this gyroscopic flow pattern exists in the surface ocean. It's detectable down to about 100 meters water depth, sometimes a little bit deeper, but it really drops off very significantly as we go down with depth. And the strongest currents are right at the surface where winds are interacting with the sea surface. Okay, so now let's think about moving away from the surface into the interior of our holding tank reservoirs. We've already talked a little bit about the interior, quote unquote, of the atmosphere. Now we're going to look at the bodies of water. So in fresh bodies of water, it turns out the density is largely driven by temperature, right? Heating from above, cooler down below, that causes stratification. And what causes the stratification to be counteracted and overturning circulation to happen are seasonal changes in temperature patterns at the surface, right? So as we go from summer into winter, we go from warm to cool conditions, we can cross over that point of the 4 degrees C maximum density and have cooler water at the surface, and this will cause convection. In salt bodies of water, it's more complicated because the density is a function of both temperature and salinity. And we'll see in a moment, the saltiest places in the oceans also happen to be the warmest places in the oceans. And yet that water is still right up there at the surface. I'm talking about surface water now. And so therefore, the heat content seems to win out relative to the salt content because we have such saline water near the surface. But the actual density stratification in the ocean happens because of a combination of salt and heat content. So when we look in bodies of water that are stratified, we find basically 3 layers: an upper layer, an internal layer, and something called a mixed layer, which is the interface between the upper and lower layers. This mixed layer will have a range of properties that go from something like the surface layer at the top of this mixed layer to something like the deep layer at the bottom of the mixed layer. And it usually happens along a gradient. The thickness of it depends a lot on various parameters, such as the variations in density and the forcing functions for the currents that we have in the first place. So the mixed layer is often much thicker, maybe a whole kilometer thick in the oceans, and maybe only tens of meters to 100 meters thick in a lake. Now, the upper part of the water that is completely mixed, okay, it can exchange gases with the atmosphere because of turbulent mixing and so forth. And everything below that into the transition zone, where we have this mixing taking place, and then into the deeper layers, is isolated from the atmosphere. So now think about all the things that we have in our atmosphere: carbon dioxide, oxygen, nitrogen, things that are involved also in biological life, especially carbon dioxide and oxygen. In upper layers of water, whether we have consumption or production of oxygen by respiration or photosynthesis, respectfully, we will pretty much always equilibrate our oxygen back up with the atmosphere because that layer is in touch with the atmosphere. Whereas once we get isolated from it into the interior body of this stratified body of water, we can no longer exchange. And so excess photosynthesis will produce extra oxygen, and excess respiration will consume extra oxygen. This will become really important later in the semester. So in this kind of layer of mixing between the so-called mixed layer in the surface and the deep layer, we have a gradient of conditions. When it's temperature, we call this gradient the thermocline. When it's density, we call this temperature the pycnocline. When it's salt content, we call it the halocline. A cline is basically just a change in parameters with depth, a dA, dz, where z is depth and a is the parameter that we're looking at. The deep layer that sits below the thermocline or the pycnocline or the halocline or what have you can remain out of contact with the atmosphere for a long time. In lakes, it can be months, but in the oceans, it can be thousands of years. So this is now a graph looking up the center of the Atlantic Ocean along a fictitious line, because you can't really draw a straight line. You have to kind of zigzag it around Europe and Africa and so forth, between nearly, the sort of Arctic Circle in the north and the Antarctic Circle in the south, 60 degrees north and south. If you look in the center of the oceans between 40 degrees north and south, you'll see really simple layering. There's a mixed layer on top, there's a pycnocline, and there's a deep layer. And this continues up until about 50 degrees north. And then you'll see that what we call the mixed layer at lower latitudes basically ends up having the same composition as the deep layer. It has the same density as the deep layer. And so we can have exchange. It takes some time, but we can have exchange between the atmosphere when we're in very northern latitudes and very southern latitudes and what's in the deep layer. We'll talk about this later. One of the ways we know how fast this goes, we can look at chemicals like freons, which were invented by humans in the 40s and put into use for refrigeration and air conditioning and underarm deodorant and so forth in the late 40s. And these are chemicals that didn't exist on Earth. We can find them in the deepest part of the deep water in the extreme North Atlantic, which tells us that it only takes something like a half of a century. This was detected all the way back in the 90s to get all the way from the surface down to deeper waters. And one thing I want to point out about this diagram is it only goes from a depth of the surface to 1,500 meters. Everything below 1,500 meters is also deep layer. And the average depth of the oceans, in case you're wondering, is about 4 kilometers. There's a lot of diagram that's chopped off the bottom here that you're just not seeing, but these freons have made it all the way down to 4K in just a half a century. So that gives you an idea of how fast those currents go. This also happens to be the primary way we can take carbon dioxide out of the atmosphere and equilibrate it into the ocean to help mitigate the impacts of anthropogenic greenhouse gas loading. And because this only happens over a small part of the ocean, the rest of the exchange of carbon dioxide is basically stuck in that mixed layer that's just floating on top. The oceans become much less effective at taking CO2 out of the atmosphere on a short time scale than we would like. So this is a diagram of stratification in a continental shelf location. We can see we go from 0 degrees or 0 meters depth to 200 meters depth on the y-axis. We can see the salt content and the temperature. The salt content is across the bottom. These are in parts per mil. A per mil is basically 0.1%. And so just like I mentioned before, average seawater has a value of 34 parts per mil. So this, scale across the x-axis on the bottom, which is what the blue dots refer to, goes from 33 to 35. And you can see there's a smooth variation in salt content at about 33.4 or so for the first 20 meters of depth in this body of water. Then we go through a halocline where it changes a lot over, maybe another sort of 50 or 60 meters of depth. And then it becomes constant with depth at a value of about 34.7. We also see this variation in temperature. In the mixed layer, it's constant at about 27 or 8 degrees C. In the deep layer, it's constant at a value of about, 15 degrees C. And we have the thermocline where it varies very rapidly. So these changes in temperature and salt content cause that surface water to be less dense than the water beneath it. And those two things to act as sub-reservoirs in the ocean, the deep water and the shallow water. So these are some diagrams from the text. I've taken the one for the lake and just expanded it to make a version for the oceans. And in lakes, where we have this kind of stratification, limnologists, those are people who study lakes, give the upper layer or the mixed layer the term epilimnion, and the deep layer, the stratified part that's isolated from the atmosphere, the hypolimnion. And the area in between is called the thermocline. Now, oceanographers are not nearly as creative. They call the surface layer, the equivalent of the epilimnion, the surface layer. And they call the deep layer, the equivalent of the hypolimnion, the deep layer. There's also an intermediate zone, which is the equivalent of the thermocline, which is stretched out over a greater depth. And I'll leave this to you to start to look at some of the things that are on this diagram, but I just want you to think a little bit about, you can see arrows for oxygen and carbon dioxide exchange with the atmosphere. That only happens in the surface layer or the epilimnion because those bottom layers are isolated. We also have things like photosynthesis, which is shown there, or respiration, which would be the reverse reaction. And as I've already alluded to, those affect compositions in the surface layer. Now, interestingly enough, photosynthesis also requires light. Respiration doesn't, but photosynthesis does. So if we're making food and we're producing oxygen, this is only going to happen in a body of water as far as light can go down. In most bodies of water, light can penetrate, if it's not too, particulate rich, about 200 meters. In some cases, a little bit more, in some cases, a little bit less, which is generally deeper than the level of stratification in many places, except perhaps the very center of the oceans, which means that we can sustain a little bit of photosynthesis below the thermocline, but the vast majority of it, because the amount of light that we have decreases with depth, so that it becomes much and much less efficient as we go down with depth. The vast majority of photosynthesis happens in the epilimnion, whereas the vast majority of respiration in bodies of water happens in the hypolimnion or the intermediate and deep waters for the ocean. This means in those parts of the water that are isolated from exchange with the atmosphere, we have the ability to consume oxygen and produce carbon dioxide. This makes the water conditions change characteristics very dramatically. We'll talk about this more as it comes along. The addition of carbon dioxide, for instance, being a weak acid, changes the pH structure of the water, and the change in the amount of oxygen changes the concentration of oxygen sensitive chemicals, as well as can affect oxygen sensitive organisms. We also have all sorts of fluxes in and out of these bodies of water. Some of them happen only into epilimnion or hypolimnion, or surface and deep water for the oceans. Some of them happen in both places. And again, a few processes are highlighted on this slide. Now let's talk about mixing when something breaks the stratification. In lakes, this has to do with temperature changes that are seasonal. I want you to think about starting in the summer where the water is relatively warm. So think about 30 degrees on this XY diagram of temperature versus density. We start to cool as we go into the autumn. And so the temperature gets colder and the density goes up. We reach a maximum at 4 degrees C. At some point, the water at the surface is going to be more dense than the water just beneath it, and it's going to displace it by buoyancy forces combined with gravity and cause an overturning circulation. Now, another thing can happen as we continue to cool into winter. If we're in a temperate region where it freezes on the surface, then as we start to go from 4 degrees C down towards zero, the water actually becomes less dense, okay? Then when it freezes, it jumps down and becomes much less dense. You can see here about 0.916 or 7 for density. But then when we go into the spring and that ice very first melts, it melts at 0 degrees C. So that water is again going to be a little bit less dense than the water that's sitting just beneath it. It's going to cause another overturning circulation. So this causes stratification that happens in temperate regional lakes and mixing that happens twice a year. And so these are just some other diagrams showing you the density relationships between freshwater and salt water. This maximum goes away when we get into salt water like the ocean. So the oceans don't circulate by this mechanism. I just kind of wanted to highlight that point to you. So this is a diagram that shows you the spring and fall turnovers for a lake, and then the conditions during summer and winter stratification for basically two parameters: temperature, which is shown in red, and DO, which stands for dissolved oxygen. Now, there's two variations of what happens during stratification, and I'm going to highlight these for you separately. One of them are in oligotrophic lakes. We will talk about this term a lot. An oligotrophic lake is a lake that is primarily not driven in composition by biological activities. It can have a little bit of photosynthesis and respiration, but not very much, which means that the oxygen concentration is primarily driven by inorganic chemistry, meaning the exchange of oxygen with the atmosphere and the surface of the stratified body of water. In the lower panel, we see something called eutrophic. Eutrophic is an extreme. It's a biologically driven lake where we have a huge amount of photosynthesis in the surface water due to very high concentration of fertilizer chemicals, primarily nitrogen and phosphorus. And in the deep water, we have a lot of respiration because as the photosynthesizing organisms that live in the surface water die, their bodies fall down into the deeper part of the lake, the hypolimnion, where respiring organisms are waiting to consume that organic matter. When they consume organic matter, they also consume oxygen. They pull the oxygen concentration down. We will talk about these processes in a lot more detail coming up in a couple of weeks. But now I'm going to walk you through the upper part of this diagram. So during mixing events, temperature and oxygen are constant. And then during stratification in the summer, the surface body of part of the body of water warms up. So we get this temperature profile, where it's warmer on top and cooler on the bottom. And we see an inverted dissolved oxygen profile. And you might say, well, why is that? It's because as the surface body of the body of water warmed up, the solubility of oxygen went down. Okay, and so some of the oxygen was lost from the surface. It's not lost from the deep water because the deep water is isolated from the atmosphere. So we actually have more oxygen in the deep water than the shallow water. Then we go into the fall overturn, and again, everything's mixed and homogeneous with depth. And then during the winter overturn, you can see the temperature profile and a slight uptick in oxygen associated with the somewhat lower temperatures in the upper part of the water column. Now, it's very different in the eutrophic lake with all the biological activity. During the two turnovers, we have the same condition, but during stratification, whereas the temperature profile looks exactly the same as it did on the preceding slide, we now see the oxygen concentration go down to 0. That's because without the exchange of oxygen from the deep water to the surface, and the very high amount of respiration that's happening, the oxygen can be pulled all the way down to 0, which causes very dramatic effects. We will talk about eutrophic lakes for a whole week later in the semester. I also want to emphasize to you that there's actually a transition that goes from an oligotrophic to a eutrophic lake. It's not binary. There's actually a natural process that moves waters in lakes from oligotrophic to eutrophic over periods of time of thousands of years for most lakes. Humans have greatly enhanced the rate of this process by dumping a lot of fertilizer chemicals into the environment, and they come in all sorts of different forms. Things we put on agricultural fields, untreated sewage. It happens in the oceans. It happens in lakes. We'll talk about this in great detail. In the process of what we call cultural eutrophication can happen in just decades to centuries. And again, this is partly why this becomes an issue, is because of the way stratification manifests itself in bodies of water. So now this is just a profile of dissolved oxygen concentration in a eutrophic stratified lake in Minnesota and temperature. You can see 4 lines on this diagram, open symbols, closed symbols, etc. The legend is across the bottom. This starts at 6 p.m. in the evening on the 29th of August in 1999. Then we have measurements 12 hours later, followed by, 6 hours later, 6 hours later, and 6 hours later. So this is, basically over the course of about a day, we can see how the oxygen concentration during a mixing event evolves into place. That's the final condition, these open circles, starting from something that was highly depleted in the hypolimnion due to this process of eutrophication. And so this happens twice a year, and the whole lake mixes out. The problem is that each time this cycle happens, we concentrate more nutrients into the surface water, and we make the depletion of oxygen during the stratification periods that much more extreme. Now let's talk about the oceans as our final topic. This is another diagram with a little bit more detail. It shows you full ocean depth now going down to about 5,000 meters. Again, starting, in the Antarctic Circle in the south, which is on the left-hand side of the diagram, kind of moving across to about 80 degrees, so closer to the pole, not quite the pole, in the north, and that's the right side of the diagram. And you can see in the upper diagram, we've got temperature. Those are isotherms, lines of equal temperature. And in the bottom diagram, we have salinity. In the top part of the diagram, we see much like we saw on a few slides ago, where there's a simple layering through most of the oceans in the temperate region between 40 degrees north and south, where it's basically hotter on top and cooler on the bottom, and it just kind of, progressively gets cooler as we go down. Now, a salt content is a little bit more complicated. In the surface waters, we have the competing effects of evaporation and precipitation, which causes variations in salt content in surface waters. But then at depth, we also have water that enters into the ocean from isolated basins. Those basins include things like the Mediterranean Sea and the Labrador Sea and the Caribbean Sea. And because those act as sub-reservoirs, they can collect water in them that's a little bit more or less salty and a little bit more hotter or cooler temperature than the main Atlantic Ocean. And so as these waters spill into the Atlantic Ocean themselves, they form identifiable layers. You can see labels on here, for instance, for Mediterranean seawater, North Atlantic deep water, Antarctic bottom water, Antarctic intermediate water. There are many other layers which we can identify based on their sources. Interestingly enough, as deep water moves out of the Atlantic Ocean into the Indian Ocean and into the Pacific Ocean, these layers tend to mix with each other and smooth out. But so the densest water in the oceans is obviously at the bottom. But if you look here carefully, you will see that the salt content measured in salinity units across the bottom are in units, these are also, per mill units. They're just quite 30, not quite 35, 34.65, 0.7, 0.8, for instance. And we have much saltier water at the surface. But because that water is also much warmer, as we learn in the upper diagram, those very salty waters don't sink down to the bottom. And this is what the thermocline looks like, the temperature variation on average over full ocean depth in the Atlantic Ocean. And then that's on the left. And on the right, you can see it sort of pulled apart for polar, tropical, and temperate. And you see how there's very little temperature variation in the polar regions. This is what allows the water masses in the very high latitudes in the deep water and the surface water to exchange with each other. It's that similarity in temperature which causes them to have similarity of density and therefore vertical currents that can cause exchange between the atmosphere and the deep water. Pretty much everywhere else in the ocean where we've got that significant thermocline, we don't have vertical transport from the surface layer into the deep layers. So this is just a diagram from which you can calculate the density of seawater. Those are shown as iso lines, isopycnals, these contours in the diagram on a plot of temperature versus salt content. And it's a little bit hard to read, but in fact, the saltiest and warmest waters in the oceans end up not being the most dense, as we saw on the previous slide. And there's some combination of being just salty enough and also being really cold that makes waters densest on this diagram. So these are plots of salt content and salinity on average in the oceans, color-coded. So the warm colors are high values and the cool colors are low values. And so you can see where from a perspective of temperature in the left diagram, where the water would be densest is where I've given the arrows, where it's coolest. And if we go to the right diagram, ignoring temperature for a minute, if we just look at salt content, where we might expect the water to be densest is at low latitudes, because that's where it's saltiest. But it turns out, as I've mentioned before, because that water is also warm, it ends up not being as dense. So when we look at a plot of density, which is a combination of salt and temperature, we find that the densest water content forms in those high latitudes in both the northern and southern hemisphere. This is what sets up oceanic circulation, because these very dense waters that are found near the surface can sink and set up deep ocean currents. Now, I ended last time by showing you this slide. I'm just going to talk about it now in a little bit more detail. This is basically what we call the oceanic conveyor belt. Look on the upper left and you'll see blue arrows. This represents the direction of deep ocean water flow out of the Atlantic into the Indian Ocean and into the Pacific Ocean, and then return flow where water rises up to the surface in the northern Indian Ocean, the northern Pacific Ocean as well, and then return flow on the surface. And this is on top of the gyroscopic flow we talked about. This is a net flow pattern. There's a little bit more detail if you look in the diagram on the right, where we see where it says source. There's source water is basically where the very cold and sort of salty water that exists in the northern hemisphere, when it freezes over, makes sea ice in the wintertime. That sea ice excludes salt, so it makes the water that's beneath the sea ice just a little bit saltier enough to get dense and to sink down to the bottom of the Atlantic Ocean. some of that water comes back in the Southern Ocean, and during the winter time down there sits under the ice sheet in the Weddell Sea, and therefore also gets salty, sinks again, and then forms the deep water circulation. Now you can imagine if we start to heat up the oceans a lot through climate change so that we don't get sea ice anymore, we may change the circulation pattern. And this is one of the many things that people worry about with respect to global warming. You can also imagine that during ice ages, when there was much more ice covering much more of the northern and southern hemisphere, this circulation pattern was different. So I just want to emphasize that the pattern you see here is the modern pattern, but it hasn't always existed exactly the same in the past. Now, interestingly enough, if we follow deep water masses along this circuit into the North Pacific, and we date the deep water masses that are isolated from the atmosphere, we find ages anywhere from about 1500 to 1800 years by radiocarbon dating of the dissolved bicarbonate. That tells us about how long it currently takes for water to make this circuit. Now, finally, you'll see a cutaway. This is a cross section of how water moves through the deep ocean circulation. And if you look, you'll see some places where water rises back to the surface. You'll see them now up above as green circles. These are areas of focused upwelling. There are upflow zones in various places of the ocean, but these particular locations have a very high upflow zone, which takes water with deep water characteristics, which includes having a lot of nutrients and low oxygen, and brings it back into the photic zone, which makes them very rich in terms of their biological activity. We'll again talk about that more later in the semester. This is just another diagram of that conveyor belt with a kind of slightly fancier look to it, kind of showing you what it looks like today. Finally, just one other point I want to mention, which is what we call basin to basin fractionation. The flow pattern in the Atlantic Ocean is out along the bottom and in along the top, and the flow pattern in the Pacific is in along the bottom and out along the top. And this causes many differences in composition, including the relative depth to which calcium carbonate rich sediments can be deposited, as well as oceanic productivity. And we will talk about these parameters as well later on in the semester, but I did want to point this out and also point out that this, what we call basin to basin fractionation, did not always exist in the past. We think, for instance, the Isthmus of Panama, which separates the Pacific and the Atlantic Oceans, only closed up between 20 and 25 million years ago. And before that, water could flow back and forth between them. And so this condition didn't exist. And this is something that we learned by looking at stacks of sediments recovered from each of those ocean basins. So that's what I had to say today. I realize this is a little bit quicker than I would have done it in class. Hopefully this isn't too quick, and this is the better option than giving you the video I recorded live that had these unideal camera angle for part of the time.